For the orbitals, the shape of the orbital, like, you said that that's basically like its house. So like for the P, like the dumbbell orbital, there'd be 3 of them all on one level.
Yeah,
one
yeah,
sub-level, and they're,
See,
like,
they would be comparable in size.
So like one of 3 of those would all be like on one sub-level together.
Yeah,
So
yeah.
they're just the house, it's not the actual orbit. Like that's not the shape
Each
of the
one
orbit,
of these
that's the
is
shape of
referred
the
to as
house.
an orbital.
But that's like the shape of like what's
That's their
in it,
bedroom.
not the
Yeah,
actual
you've
orbit.
got a freaked out architect doing this work. Okay, so here's a better rendition, and this is in your book on page 155. Also, Al does a good job of these pictures and animations and stuff too. Here it is along the x-axis, so that's what I've so crudely drawn over there. This would be one orbital, or bedroom, or house, whatever. Up to 2 electrons can live in this volume, in the volume.
So that dumbbell thing is not a physical entity, I guess is what I'm saying,
It's
because
a
you're calling it
volume.
a volume.
Yeah, it's a volume.
So the
It's a
dumbbell
volume.
is not actually like a physical
No.
thing that you could
No.
touch if you could.
It's just,
I mean,
it's
small, you couldn't touch
it's
it,
the
but.
volume that this
Yeah.
guy can be found in. So there's no like borders or anything.
So it's actually like invisible. It's not, it's
Yeah.
there, but it's not there.
That's where you find those electrons doing their thing in that shape of a volume.
Right.
I'm trying to.
And here's the piece of Y, and here's the piece of Z. Yeah, and
You said 2 electrons can live in a P,
in one piece, yeah.
in 1 P?
And
Okay.
when I say one, I mean one of them, not, there is no one, see, that's what's difficult with our language. 1 P, there is no 1 P sublevel, but there, we talk about 1 P orbital.
Yeah.
That's why I was careful, so I wasn't too careful, I put 1, 3, 5, 7. It'd probably been better if I'd written out the word,
So-
1 and 3.
So since there's two shapes, I guess, to P orbital, like you see what I mean? So could like 2 electrons have like be on one side and none be on the other?
Yep.
Okay.
All we know is there's a high probability that up to 2 electrons, doesn't have to be 2, it can be empty. And then as Nina says, it's nothing, but you could have 2. They could both
So
be up
it'd be
here,
2.
they could both be down here, one up here, one down there. Because we think electrons move. We don't understand how they move because electrons are so tiny. If you tried to measure them, like if you zapped them with energy like X-ray or something, you'd blow them out of the park. It would be like me taking roll. If I were blindfolded at the first of the hour to take roll and I've got a gun, and I point it over there at Bruce, and I'm going to shoot. And if I hear him scream, I go, Bruce is here today. By doing that, I may know he's there, but I have destroyed the situation, and probably I won't even have a chance to get a second shot off because you guys aren't hanging around with this crazy woman up here blindfolded with a gun. So when we aim at the atom to find out what the electrons are doing, we ruin the situation. And so that's why it's probability. What we believe is electrons, like here's an electron. It's moving from place to place. We don't quite understand how, because ordinary physics doesn't really describe this. This is why we switched from Newton-type physics from the 1600s to, Einstein and all the guys at the first of the 20th century. And so you have different rules or laws for these tiny little particles. That's why they call it quantum mechanics. Okay, so they think an electron is moving from place to place. They don't really know how. They also have good evidence that, or at least it seems as though, not only is it moving from place to place, it's also rotating on its axis. So it's going moving around, like a bee on drugs or something. It's moving from place to place, but it's also spinning on its axis. Okay, so we put all the P's together, and that would be one sub-level. Okay, now, I want you just to know shape. If I say, what's the shape of an S, you're going to say a sphere. If I say, what's the shape of a P, you're going to say a dumbbell. Okay, then, let me see if I can get this last part up here. Can't do it well. Okay, this is down at the bottom of the page, and it's too far down. Let me see if I can. Okay, I can't get that any higher, but at the bottom of the page, see, up at the top we have the S's and then we have the P's. D's are just more complex. It's like two P's put together. So here's one D orbital. It's like a four-leaf clover. And so they have that superimposed on an axis here as well. So this would be one of them, and this would be a second, and then they have pictures of the third. I don't care so much about the D's because they get more and more complex, but their shape is like a four-leaf clover. So those are the shapes. Now, let's try to put this story kind of together. Let me go back to a diagram that I answered one of Brittany's questions with. I was drawing this before. These are called box diagrams. Sometimes they're referred to as block diagrams. It's unfortunate there's so many different words for the same thing. Here on a box diagram, we can pretend the nucleus is right here, increasing energy this way, and each box now represents an orbital. Remember when I first drew this, I said don't worry about why I'm drawing 3 or 5 of them together. This is the 1s, here's the 2s, a little bit higher in energy, the 2p. That's the 2p sublevel, but it's made up of 3 orbitals, so I draw 3 boxes. And then we have the 3s, we have the 3p, 4s sneaks in, it jumps out of its place in line, and that's the 3d, and I'm not going to go any further. This is sometimes very helpful for people to see a picture of it, then you get really tired of doing these, because every time you do one, you got to recreate this. You need a rubber stamp or something. If we were going to do, like a half an hour ago, this is what we were doing half an hour or 45 minutes ago. I have hydrogen. It's got 1 electron, and what I would say is, what is the electron configuration? And what would you all have told me a half an hour ago? 1s, how many? 1. Okay, that's the electron configuration. Here's a new question. Draw for me the box diagram, or what does the box diagram for hydrogen look like? And here's the convention. We use a half arrow up to represent an electron, or a half arrow down. The first one you put into an orbital, by convention, it's an arrow up. The second one in, an arrow down. And so, the box diagram for hydrogen would be like that. Half arrow up, it's the first guy in. What's that? Yeah, half arrow up. By convention, although I've seen it both ways.
What are we doing?
Okay, that's a picture, and that picture, see the arrow, the little half arrow there, represents an electron. So I've got a visual there of what that electron is doing. It's on the first major energy level, it's in an s sublevel, it's in an s orbital. This box diagram has major level, the sublevel, and the orbital there. Now here's, what if I were moving up to helium? If I asked you a half an hour ago, what's the electron configuration, you all would say 1s2. Think back. 45 minutes ago, I would have said that, and there would have been silence. And you'd go, oh my God, what is that stuff? And now you're just 1s2. No problem. Okay, but here, I want the box diagram. Okay, since I've got a whiteboard, I can cheat. Okay, I put the first electron in, I put the second electron in. And so we have one half arrow up, half arrow down. And we say those electrons are paired. Hydrogen has 1 unpaired electron. That is, it had a guy hanging out by itself. Okay, helium has no unpaired electrons, and number of unpaired electrons is an important idea. I know we're running out of time, but I want to be sure we get one more thing in here. I have carbon. I have 6 electrons. Russell, hit the configuration for me. Not this, electron configuration.
1s2,
Mhm.
2s2, and then 2p4. No, 2.
2. Okay, there's 6. Okay, I want the box diagram now. Here's the first 2. Here's the second 2. Then, what do I do with the next 2? Are they both going to be in here, or do they get spread out? What we find, they spread out. And this is referred to as Hund's rule. And let me tell you a crazy story, even if I run this over a minute or so. This is our Electron Hotel. Okay, our hotel has no elevator and no bellboys. If you come, you carry your own luggage and you carry it up the stairs. Okay, our first guest, let me just... Okay, I don't know, it's an all-male hotel, all-female hotel, no hanky-panky going on here. This is just for the analogy. Okay, our first guest comes in, and we say, we have this empty room on the first floor. You don't even have to climb any stairs. Good, great, I'll take it. Second guest comes. Okay, you got a choice. You can haul your luggage up a flight of stairs, or you can share a room. It's the same price either way. Well, the guy goes, I'd rather share a room, because it costs me energy to carry it up the flight of stairs. Okay, the third guest comes. Tough luck, you got to climb the flight of stairs. Okay, now the fourth guy comes. He's got that choice. You can climb 2 flights of stairs to get to here and have a private room, or you can share and only have to climb 1 flight of stairs. Well, he's lazy. He'll go there. Okay, then, let's see, our fifth guy comes. No choice, tough luck, you got to climb up 2 flights of stairs and you can have a private room right there. Okay, now here's the deal breaker. The next guy that comes in, okay, tough luck, you got to climb 2 flights of stairs. However, you may share a room or you may have a private room, same price. He goes, hey, I want a private room. That's called Hund's rule. H-U-N-D, Hund's rule. If there is an orbital of the same energy, vacant, you're going to go for it. You want your private room. And so, that's a big issue when you talk about how many unpaired electrons somebody has. You got to know Hund's rule. Because carbon, how many unpaired electrons does it have? How many unpaired does carbon have? What do you see? Unpaired means got a room alone. 2 unpaired. Yeah. Okay. Let me tell you one other thing, if you can stand it. You guys are tired and I'm having a great time up here. Okay, why do we go half arrow up and half arrow down? Okay, because we feel like electrons spin on their axis, and this is from a physics class. Okay, how do 2 negative things tolerate each other to stay in the same volume? Okay, if you have a negative or positive charged particle, for that matter, if you have a charged particle that's spinning on its axis, it sets up a little magnetic field. Okay, if it's spinning counterclockwise, it sets up a certain magnetic field. If it goes clockwise, it sets up another type of magnetic field where they can tolerate each other. And what I visualize in my head, back in the days when I had 2 male cats, okay, what if I had to take them to the bed on the same day? Okay, they don't like to be in the same carrier, because those tomcats hated each other. Okay, so I had this vision. How could you get them in the same volume? Get them to stand up, twirl, and they'd both be so dizzy they wouldn't notice there's another male cat in the cage. And so, electrons, counterclockwise, clockwise, that's what the half arrow up and half arrow down implies. If there's something a little different about them, they're spinning in the opposite direction. Okay, now I've run us 3 minutes over, so 11:33, back in here.